Hi guys, and welcome to part 2 of current electricity. So today we're going to talk a bit about the different, vocabulary that goes into current electricity, and everyone's favorite, we're going to look at some of the math. Woo! So let's hop in. Current electricity, well, let's review. Static electricity is electricity that's staying still, right, or doing a short jump. Current electricity is our electricity that's constantly moving and controlled. It's in a circuit of some sort. Both can supply a charge to an object, but static electricity gives all the charge at once, right? It jumps like a spark. Our current electricity tends to give charge over a longer period of time. And so what this looks like would be something like this. So you can see that the battery is pushing electrons. They're moving around the circuit, and you can see that the charge is going through the battery slowly. Now, the fun thing about this website, and you guys get a chance to play with this in the next couple of days here, but you can actually click on the battery and increase the voltage. What happens if I increase the voltage? Oh, charges move faster, light bulb glows brighter. If I reduce the voltage, electrons, well, not 0 volts. 0 volts means no electrons. Come on, give me a little push. There we go. 3 volts. Electrons move really slow, and my bulb barely glows. But is there a way to, calculate that stuff? How fast the electrons will go? How much push I'm going to get? How much the light bulb is going to slow down the flow of electricity? Well, of course there is. But let's start talking about some of these words first. Because there's a lot of electrons that flow in electronic devices, we're not going to count individual electrons. That would be crazy. So we've just basically made up a word called a Coulomb. Now, this word doesn't have to scare you. Think about if I tell you a pear, how much is that? It's 2, right? What if I said I've got a few of something? It's 3-ish. What if I said I got a dozen donuts? How many do I have? I've got 12. It's just a word that means a number, right? That's what a Coulomb is. A Coulomb of charge, it's just a number. Just so happens to be a very, 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 very big number. 6.25 times 10 to the 18. What that means is take 6.25 and move your decimal 18 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You can see why we don't write that number out every time. Guarantee you miss a 0 at least once. So we use this scientific notation to write that really, really, really big number down. Now, this should also give you an idea of how small electrons are, right? Like when I get a shock, it's pretty easy to move that many electrons. So 1 Coulomb of charge is 6.25 times 10 to the power 18 electrons. So if I told you, for example, we plug something in and 2.5 coulombs of charge move, how many electrons is that? Well, it's 1 coulomb's worth times 2.5. Now, here's my challenge to you guys. Do this on your calculator. Actually, pause it right now. Try to figure it out, because a lot of people don't know where the exponent button on their calculator is. A couple hints I'll give you guys. The exponent button sometimes looks like this. Sometimes it looks like this. And there are other ones out there too, but those are kind of the 2 most common ones I think you'll find. Give it a shot. See if you can calculate this. If you can't, get your teacher to help you find the button on your calculator. Hold it up to your screen. Do whatever you need to do. Go find them and ask. Find your exponent button. You're going to need to use it. All right. So you had a second there. Hopefully you found your exponent button. You did the calculation. You checked with your teacher. The answer you should have got 1.5625 times 10 to the 19. Some of you might have seen your calculator saying 1.5625 E19. That means the same thing. E is just essentially exponent, 10 to the exponent 19. Hopefully you guys have done exponents in math already. So what we do, now that we know what coulombs are and what charge is, if I want to figure out how much electricity is flowing, if I want to find the current, I use the formula I equals Q over T, where Q is your electric charge in coulombs. So I is your current. It's how many coulombs, and T is in time per second. There we go. So I equals Q over T is what the formula is. If you look at the units, what we're doing is we're finding current by dividing coulombs by seconds. So you're going to work with I equals Q over T. Excuse me. Always double check your units. Charge needs to be measured in coulombs, and it almost always is. But more importantly, time needs to be measured in seconds. That's a science thing. You almost always find time measured in seconds. That's the way that these formulas are designed to work with seconds. So if it gives you like, hey, that took 5 minutes, you're going to have to change 5 minutes into seconds, timesing it by 60. So let's do it. What current? So here's how we set these word problems up, guys. What current? Current equals what? Passes through a light bulb that has 82.5 coulombs. What are 82.5 coulombs again? Coulombs is a measure. Oh, yeah. Coulombs is a measure of charge. That was Q. Over 2.5 minutes. Time equals 2.5 minutes. But wait a minute, Mr. Burns. You're all screaming at your screens right now. You can't keep time in minutes. You guys are right. Good job. There are 60 seconds in 1 minute. So you times it by 60 seconds per minute. My time is actually 150 seconds. All right. So now I know what I need to find and the bits of information I've got. I got 2 out of 3. That's good enough. I can work with that. Do I know a formula that has I and Q and T in it? Well, I mean, I hope so. We've only learned one formula, so it better work, right? There we go. So I, which I don't know, equals Q over, oh, whoops, that's coulombs, not Qs, over T. And so that's literally what you do. 82.5 divided by 150. So that's my current. What is current measured in? Let's go back and check. Current is measured in amperes, amps, A. So when you hear someone say like, hey, that's a 10 amp circuit, that means you could get 10 coulombs moving every second. Amps is coulombs per second. So that is a lot of charge, right? 10 times that massive number every second? That's wild. So amps can be very dangerous. You don't want big amp numbers or you're in trouble. That's a lot of charge. Here, I'll box my final answer. Always a good practice. So, quick recap. To do a word problem. 1, write down what you do and do not know. 2, find a formula that fits the things you do and do not know. 3, plug in what you know into the formula. And 4, plug and chug. Plug in your numbers and chug away at it till you've solved the actual problem. Do the math. So let's try it again. One more shot here. What charge? Oh, what? Sorry. Charge. Charge was Q. That was coulombs. I was going to use C for coulombs. What number of coulombs go through a stove if it's got 20 amps? Oh, amps was current, right? All right. And if that flows for half an hour, time equals 30 minutes. No, don't like that. Got to change it into seconds. So you take your calculator, you do 60 times 30. 1,800 seconds. Okay. So I got 2 out of 3. I read out my formula. Q over T. All right. I know. It's a 20. Q, I don't know. Time, I do know. All right. Oh, man, fractions. Everyone's favorite, right? How do I get a number out of the denominator of a fraction? I want to get this question mark on its own. That's the goal. That's how you solve algebra. That's how you solve these math problems. So how do I get a number out of the denominator of a fraction? Well, it's math. I got to do the opposite of something, right? What's the opposite of a divide? It's a times. So if I was dividing the question mark by 1800 and I want to get rid of it, I can times by 1800. And those two things will cancel out. But what's the rule of math? If I times by 1800 on one side, oh yeah, I have to times by 1800 on the other side. Anything that happens on one side of the equal sign has to happen on the other. So I do 1800 times 20, and I'm left with 36,000 as my Q, which was coulombs. 36,000 coulombs. That's a huge number, but think about it. I'm running 20 coulombs a second for 1,800 seconds. That's a half an hour worth of energy. That is a lot of electricity. Now, luckily, it's not asking me for a number of electrons because that number would be crazy big. But looks like we've got 36,000 coulombs traveling in that half hour. All right, last one, I promise. While charging, your phone draws 0.5 amps. That's my current. Giving the battery a charge of 2,250 coulombs. Charge is Q. How long is your phone plugged in for? So when I solve this, because I'm going to be solving for T, should it give me hours, minutes, or seconds? What do you guys think? Think about it for a sec. Seconds, right? These formulas science always spits out time in seconds. All right. So I got the stuff I know. I write my formula. I plug in what I know. Oh man, I got a question mark in the denominator now? How do I get rid of something in the bottom of a fraction? Well, it's the same rules. You multiply by it. I can multiply by a question mark if I want. But if I do it on one side, I got to do it on the other side. So what am I left with? 0.5 times, I don't know, equals 2250. So now how do I get the question mark on its own? Well, what's the opposite of a times? Opposite of a times is a divide. If I divide one side by 0.5, I got to divide the other side by 0.5. Those cancel out. And I'm left with my question mark being, and again, you can put an X in there if you like X better because you're more of like a math brain person. And of course, I'm doing time, so I know my units are in seconds. Yeah, if you like X instead of the question mark, I just use question mark as a placeholder. You put a happy face in there for all I care. It's just a symbol representing something I don't know yet, which that's what question mark means to me. But if you're a very mathy person, you could feel free to solve it with X, solve it with happy face. It'll give you the same answer no matter what. You'll do the same steps. So that's the three different things you could solve with current. But wait, that simulator, I used voltage. What the heck is voltage then, Mr. Burns? You just go me amps. All right. Current electricity, right? We move electrons from a positive side to the negative side, or more likely from the negative side to the positive side. Now, this creates electric current. If I want to move something through the circuit, though, it takes energy. It's like if I got a ball and I got to move that ball across the classroom, I got to put energy in. I got to like roll that ball over, or I got to throw the ball. If I went out in the hallway, if I had to move the ball further, I'd have to put more energy in. I'd have to throw it harder. Or maybe I put something in the way. Maybe I fill the room with water. I can still get the ball to the other end, but I just might have to shoot it out of a cannon. I just need a lot of energy to do it, right? So voltage, or sometimes it's called electric potential difference, it's used to describe how much energy you need to actually move 1 coulomb of charge from one point to another. So if I want to move a coulomb all the way around the battery, all the way around the circuit, how much energy do I need? So the voltage in an electric current can be found with this equation. Voltage is energy divided by Q. And Q is charge again. So your voltage is how much energy is needed for each coulomb of charge. Oh, that's not an F. Yoink. There we go. So V is your voltage, E is your energy, Q is your charge. So how much energy is in each section of charge? What's needed to push it all the way around that circuit? Now we measure energy in joules. So you'll hear joules a lot. We know that charge is Coulomb. We just did that one. And so if we want to see what a volt is how many joules per Coulomb. But we just, instead of calling it joules per Coulomb all the time, we just call them volts. So you can think of voltage kind of like electric gravity. And by that I mean, okay, I've got my pen here in my hand, right? If I lift it up in the air, I'm giving it gravitational energy. If I let go of this pen, it can fall to the ground. And I could use that falling to spin a turbine, or, I could throw it at somebody. I could make it hurt them, right? It could do something. It's got energy as it drops. So if it's up in the air and I drop it, it turns that gravity into moving energy because the pen wants to fall to earth. Gravity pulls it. Now, the closer that object is to the ground, the less energy it has. If I lift it up 1 centimeter off the ground and drop it, it's not going to do very much work. If it's already on the ground, it's got nothing. There's no gravitational energy. I let go of that pen when it's already on the ground, it's not going to move. The greater the gravitational potential the object has, the higher I raise it, the greater the energy that object will have if I drop it. If I lift this way up into the clouds and let go of this pen, it'll probably kill somebody by the time it hits the ground. It'll be moving so fast. It'll have so much energy. So if you think of a charge, it's kind of just like a particle that wants to fall from the negative end to the positive end of a circuit. It's like you're dropping it from the negative side to the positive side. If the positive end is very positive and the negative end is very negative, it's going to push that electron really fast. The electrical potential difference is really high. It's going to be a lot of energy moving that charge through the circuit. So an electron, or a charge, would have like a crazy amount of energy as it travels through the circuit. Now, if the negative side and the positive side were actually pretty close in terms of charge between them, then it's not going to push the electron very hard. The voltage would be low. The electron wouldn't move very fast. It wouldn't have much energy. It'd be hard to do work with it. If you want to figure out the difference between current and voltage, think about it like dump trucks. The amount of stuff a dump truck can move is how much energy is in the circuit. It's like your voltage. So a big voltage would be a big dump truck. I can carry a big load. Current is, well, the speed of your charges is like the speed of the trucks, right? I could have really, really small trucks, but if they move crazy fast, if I've got 1,000 trucks a minute going past this spot, well, I can move all kinds of dirt. Vice versa, I could have one absolutely massive truck and have it trundle along really slowly and still move a large amount of dirt, right? So you have two things that can make your circuit do energy. Dirt is the amount of energy you've got. Do some work. So you've got voltage, which is the size of the truck. It's how much energy each of those particles has. Whereas current is the speed of the trucks, how fast they're going, how fast your electrons are moving, how many of them go past the spot in a second. So if you have huge trucks, big voltage, and they're moving very fast, high current, you're going to have a ridiculous amount of energy, and it will be very dangerous. You want to, like, it says danger, high voltage. That means nothing. High voltage is not dangerous unless it's partnered with current. Either of these alone isn't, like, I could have the fastest trucks in the world, but if each truck is like the size of an eraser, they're little like Hot Wheels trucks, I'm not getting anything done, right? It can take me all day. It doesn't matter how fast those cars are going. I'm not going to move any dirt with Hot Wheels trucks. If I flip it around, if I got the biggest truck in the world, one of those huge mining things that you can like fit a house in the back of, but it travels at 1 centimeter an hour, again, I could have the biggest voltage in the world, but if my current isn't very fast, I'm not getting any work done. Same with my electrical circuit. So huge trucks at a walking pace, not much risk. That's the Van de Graaff generator. High voltage. 250,000 volts, but crazy low current. So it's not really dangerous. You feel a little zap here and there, but if that amount of electrons were flowing through me constantly, I'd have a big problem. But because it's low current, they don't move that fast, they do one little jump and they're done, you don't get a lot going, well, you're safe, just like the Van de Graaff generator. Last thing we're going to look at here is resistance. So things move through a circuit, but if you remember, in the particle model, positive charges are fixed, right? The electrons move. So if electrons are flying around, what are the positive charges doing? They're stuck there, right? They can't move. So what happens is you've got a wire with these fixed positive charges that cannot move at all. And electrons are being sent through this conductor. They're being repelled because of the voltage. And so if I want to travel as an electron, oh, I'm going to hit that one. And oh, I'm going to hit that one. And oh, I'm going to hit that one. And oh, I'm going to hit that one and hit that one. And they're going to get bumped generally. They might go backwards occasionally, but they're going to run into all of these fixed nucleuses. Nuclei? Nuclei. They're going to get hitting all these nuclei on their way through the wire. So when they bump into these atoms, the electrons slow down just a little bit and end up giving up their energy as heat or light. That's how loads work. That's how a light bulb works. That's how a toaster works. They intentionally bump into the electrons to slow them down. And we call that bumping. We call that opposition to flow resistance. How much resistance is in a wire tells you how hard it is to force electrons through, and also is an indicator of how warm it's going to get. So we measure resistance with something called an ohm. Uses the Greek letter omega, which is a fun one to draw. 1 ohm is the resistance of a wire if I put 1 volt of energy behind the charge and it can only travel at 1 amp. 1 volt matching 1 amp, that means there must be an ohm of resistance. If there was less than an ohm, the current would move faster and you'd see more amps. If there was less resistance, the current would go faster. So ohms tells you how much resistance a wire would have if it had 1 volt and it ended with a current of 1 amp. So again, resistance is what makes that light bulb glow, what makes the electric element warm up. What happens is your light bulb has a tiny narrow wire called a filament. So you've got your regular wire carrying electrons, and then it goes up into the light bulb and narrows into this tiny little teeny wire. And then goes back out into the regular wire, which is big and beefy and has lots of room. So if I've got 100 electrons flying this way, lots of room. It's like being on the highway. Life is good. All of a sudden, I need to squeeze 100 electrons through here. They're going to bump into a lot more stuff, right? So when I narrow the filament, there's a lot more resistance, and all of a sudden, this thing heats up, and it gets so hot, it starts to glow. That's how those old school incandescent light bulbs worked. That's really how your toaster works. That's why it glows red hot. The electrons lose so much energy in that tiny little wire that it heats up and glows. And I mean, they make it out of materials that are good for resistance as well and are also somewhat heat resistant. But that brings us to Ohm's Law. Another fun one to say. So how are these three then related to each other? Volts, amps, and ohms. Ohm's Law describes the mathematical relationship between them. Voltage equals your current times your resistance. This is probably one you want to jot down somewhere. This is a very handy formula. Basically what it means is, if you kept the voltage the same, 9-volt battery, I'm not going to change the voltage of the battery. If I were to increase resistance, then my current would have to go down. More obstruction in the way means an increase in resistance reduces current. And vice versa. If I drop the resistance, my current will increase. That's a math relationship called inversely proportional. Might be a handy word if you guys are heading into studying some math. So if one goes up, the other must go down. They go opposite to each other. They're kind of like a scale. You put something on the resistance end, then if you drop your resistance, the resistance end goes down, then the current end goes up. If you put the resistance ends up in the air, the current end has to go down. They're opposite of each other. So let's try it. Word problems. We're going to follow the same thing we did before. What is the current? Current equals what? In a 120 volt circuit, if there's a toaster that has 50 ohms, resistance is 50 ohms. All right, what's my formula again? V equals IR. Okay, I know V. I don't know I. I do know R. So how do I solve this? I gotta get the question mark on its own. So I take whatever's touching it. If it's times 50, I divide by 50. 120, divide by 50. My question mark gives me 2.4. Current. What's current measured in again? Oh, capital A, amps. Interesting side note, the reason it's capitalized because it's named after the guy who found it. Ampere was his name. So anything that's named after a person gets capitalized. Anything named after, like just kind of made up, is lowercased. What voltage would be needed to move 2 amps? Ugh, that's an ugly 2. Fix that. Through a 12 ohm hair dryer. All right. V equals IR. Voltage, I don't know, and it's going to be 2 times 12. Well, that's an easy one. What's 2 times 12? 24 volts. I would need I need 24 volts of potential difference to force 2 amps through a 12 ohm hairdryer. If I didn't have enough voltage, I wouldn't be moving 2 amps. It would be too slow. All right, last one. I got 4 amps of current passing through a point. I hook up a 9 volt battery. What is the resistance on the circuit? Volts, I got 9 of them. Current is 4. I don't know resistance. You should be able to solve this one by now. Divide both sides by 4. It turns out 2.25. What are the units for resistance again? Ohms. That was an ugly ohms. I like drawing those too. Oh well. So that's Ohm's laws. These are the mathematical relationships that determine how these things are related to each other and also what they are. So quick recap. Current is how many charges move per second. It's the speed of your charges. Voltage is how much energy there is per Coulomb of charge. It's basically how much energy is being used to push charges through a circuit and how much energy each charge will have. Resistance is a measurement of kind of how much the wire slows down the electrons, and you can kind of use that to figure out how hot or cold a wire is going to end up getting. So thanks for listening, guys. That wraps up today's lesson, and I'll catch you all later.